Okay, cool. Hello, everyone. So today is my great pleasure to present some of our latest work on learning to separate object sounds from videos and robot interactions. So to motivate the big picture about where we're at, because I'm from the computer vision community, now given an image like this, now visual recognition systems can tell us this is a living room, can recognize the baby, the dog, etc. But if we only focus on what we see, we actually miss a lot of other interesting ingredients of the world. For example, here is what is happening in the scene. So as you can see and hear, apart from vision, audio also provide informative cues to help us to learn about what we see. Sound can tell us about object identities, material properties of the objects, and subjects' emotion, the dynamic sources, or even the spatial environment. So there are many things that we can capitalize on once we are able to listen. So particularly in my short talk today, I want to focus on the sound of objects. So human-developed learning is a multimodal experience. Kids can quickly amass a repertoire of objects and their sounds. Similarly, our goal here is that we want to learn a representation of what different objects sound like so that we can have a joint model of how things look and how things sound. But the challenge is that in real world, the sounds of different objects does not exist in isolation, but are usually mixed together in various scenarios. So in an unlabeled video, object sounds often exist as a single audio channel that mixes all of them together. So the problem is, how can we obtain these object sound models naturally, including from unlabeled video? So particularly, I will talk about our recent work on audio-visual speech separation as an example, and it's related to the famous cocktail party effect and also the McGurk effect Professor Hart just mentioned earlier in her talk. So we formed this problem as visually guided speech separation. So given the video, we first split it into its audio stream and the visual stream. And then we detect the visual objects. Here, the two speakers. We use the visual information to guide the separation process to separate their voices. Actually, several recent work have tackled this problem, but these prior approaches all focused on learning the alignment between the speakers' lip movements and the sounds they generate. We observed that the consistency between the speaker's facial appearance and their voice is also revealing for speech separation. For example, I'm going to play a voice of from one of the speakers shown here, and you can easily tell which speaker the voice is coming from.
Alors bon, moi je suis une novice, pour le coup, j'ai jamais vu ça concrètement, mais c'est 2 mois.
This might be an extreme example because this is from you probably can easily tell it's from the second female speaker. How about this one?
People being cool, and you can see that in daily life.
You probably can also tell it's coming from the fourth speaker. So a person's gender, age, nationality, or even body weight are often visible in the face and give a price for voice qualities. For example, female speakers are often register in higher frequencies, and research also shows that a heavier person may exhibit a wider range of sound intensities. So if we have a cross-model embedding space, imagine for the second speaker, the face and the voice embeddings should be embedded close in the cross-model embedding space. And it should be far away from the embeddings of a different speaker in this cross-model embedding space. So prior work on this cross-model matching learned this kind of cross-model face-voice embeddings for the purpose of person identification. Differently, our goal is to do audio-visual speech separation, and we find that these two tasks are mutually beneficial. So our idea is to jointly learn audio-visual speech separation and cross-model face-voice embedding learning. So the better the separated audio, the cleaner it is. It will create distinctive voice tracks that can help embedding learning. And also, the better the embeddings are learned, it will provide a better vocal and facial prior that can in turn help audio-visual speech separation. So these two tasks are mutually beneficial. So that's our idea. And here's our detailed multitask framework to jointly learn audio speech separation and cross-modal face-voice embeddings. I will use some novel loss functions, mask prediction loss, speech consistency loss, cross-modal matching loss to learn audio speech separation with cross-modal consistency. Let me show you some examples of what we can get from our system. First, I will show you the original video with the speech mixture. Then I will show the separate voice for each speaker. Here's the original video.
Well, you became a superstar.
No, I did not.
Yes,
no,
you
I
did.
not. No, I
sure
did
you
not.
did. From
are
me,
you gonna,
I gave you full credit. If you're talking to me now, I gave you full credit for that.
Am I going to speak my piece or not?
Go
am
ahead.
I going to speak my piece or not?
Go ahead.
Okay, because you want to interview me. I ain't interviewing you. You want to talk to me. I don't worry about talking.
Floyd,
you want to talk
go ahead.
to me.
I'm waiting on you.
So now let's separate the voice for the left speaker.
Well, you became a superstar. Yes, you did. Sure you did. From me, I gave you full credit. If you're talking to me now, I gave you full credit for that. Go ahead. Go ahead.
Now let's separate the voice for the right speaker.
No, I did not. No, I did not. No, I did not. Are you gonna let me speak my piece? Am I gonna speak my piece? Am I gonna speak my piece or not? Am I gonna speak my piece or not? Okay, because you want to interview me. I ain't interviewing you. You want to talk to me. I don't worry about talking.
So it works pretty well. So we can also use our system to do audio speech enhancement. Here's one example. We try to suppress the background noise for a noisy speech. Here's the original video with noisy speech.
So today's talk, communication behaviour strategies, we're going to talk about over a couple of videos because there's actually quite a few tips and tricks to get through to help people with normal hearing and people who have a hearing loss or are hard of hearing. Yeah. So what are some of your tips and tricks for people who come to a noisy place like a cafe cat?
Doing audio enhancement within our system. So like this.
So today's talk, communication behaviour strategies, we're going to talk about over a couple of videos because there's actually quite a few tips and tricks to get through.
So as you can tell that most of the background noise has been suppressed and works pretty well. So we also, here are some quantitative results, and we compare to prior state-of-the-art methods on audio speech separation and on all 5 datasets. Okay, this is about audio speech separation. So our prior work also studied other objects, such as music instruments. So here I'm going to show an example where we train on over 100,000 unlabeled multi-source video clips, and then we try to separate the audio for label testing video. Here's our original video. And we separate the audio for the violin. And we can separate the audio for the flute. Okay, so what I showed just now are all sound mixtures in videos, and which are passively recorded. Next, I want to shift your attention to active scenarios where robots interact with different objects in the world with a tool. So the sound an object makes when impacted can inform a robot of the properties of objects, which may not be evident from vision. However, when the tool and the object strike each other, the resulting sound is usually some composition of both the sounds made by the tool and the sound made by the object itself. How can we separate these object sounds for robot interactions? We propose a model called deep impact, a differentiable model for rendering impact sounds of rich objects. So deep impact uses physics-based models for modeling different physical characteristics of the impact sounds of an object. So by combining this physics-based model bias with a fully differentiable renderer, we're able to use deep impact to infer physically interpretable parameters from real-world sound, such as the force profile, the object modeling impulse response, and the filtered noise and the reverberation from the environment. So we use an analysis by synthesis approach to feed an acoustic model for each object. So to model and extract parameters from this real recording shown here, we start by initializing a random series of impact forces and a random object impulse response, which are convolved to get our rounding estimate of the synthesized waveform. And we take the spectrogram of this waveform and compute the L1 loss against the ground truth spectrogram to adjust the parameters of the upstream model during the gradient descent optimization. And here we have the estimates of the extrinsic impact forces and intrinsic object impulse response, which result in the following synthesized clip. So we can feed acoustic models to each object from the sounds of multiple pairwise impacts between the different objects and tools. It can then use the acoustic models it learns to separate the sounds of these objects from each impact sound sample it hears. Okay, all right, let me show some results from separating the sounds for a steel fork and a ceramic mug. So the fork has higher pitched, under-damped components, whereas the mug has slightly lower frequency components. And here is a video of the strike. The directionality and the gain of the microphone actually already get rid of most of the noise, but there is still some robot motor noise. As you can see, a faint band across the spectrum here. After our model has fed parameters to the clip, here it is a synthesized output for the impact. So this includes all the sound components except the background noise, which models sounds such as a motor noise from the original recording. And since our model has composed its sound by feeding acoustic models for both objects, so we can turn off the mug's contribution and isolate the fork contribution to get only the model's estimate of the fork sound. Similarly, we can also separate the sounds for the mug. And along the way of synthesizing the sounds of the impacts, Deep Impact has fed an acoustic model for each object. And here I'm just going to show the separate impacts for each object. Here's a ceramic mug, the polycarbonate cup, the steel bowl, and the wood holder. As you can tell, it pretty accurately captures the different sound characteristics of these different objects of different material types. And we can also fit acoustic models for each object, for each of the tools used when striking the object. So here are the separated impact sounds for each of the tools: the ceramic chopstick, the polycarbonate spoon, the steel fork, and the wood spoon. So our model separates the sources of these pairwise impact sounds. Because we don't have the ground truth of these separate components, so as a proxy for evaluation, we can infer material properties from the separate sounds and the original sound for comparison. So we first construct a classifier to classify materials from sound and train it using a public available purely synthetic dataset of sounds. And here's a classification accuracy we get from trying to classify materials from the original audio. And here's accuracy for to model-free source separation baseline, long-lasting matrix factorization, and deep audio prior. And here is accuracy from the separate sound from using our method. It much more accurately separate the component sounds and can accurately classify its materials. Similarly, Deep Impact outperforms the baselines were being used to regress Young's modulus from the separate sounds. So estimating such properties, such material type and Young's modulus before manipulating an object can inform the robot about how it can safely and effectively be manipulated. All right, so in summary, I talked about how we can disentangle the object sounds from videos. Particularly, I talked about the visually guided speech separation with cross-modal consistency. And I talked about diff impact, which is a differentiable framework for rendering and identification of object level impact sounds. And this is joint work with the people showing here. And thanks for your attention. And that's it.